Right, so welcome everyone. Today we're very happy to have Dalimil. He's going to tell us about conformal measure spaces.
Thanks a lot, Lawrence, for the introduction. Thank you all for coming to the talk. I believe it is probably my last talk as a postdoc here at the IIS. So it's been a good round. Thanks for having me. And yeah, so I'll tell you something about conformal measure spaces, which is some work done in collaboration and in progress with James Bonifacio, Peter Kravchuk, and Shredded Pop. And somehow the basic idea of this work or of this talk is to isolate the minimal set of assumptions which lead to the conformal bootstrap. So somehow to define a mathematical object which is guaranteed to produce solutions of the conformal bootstrap. And a particular set of solutions, particular examples of these objects are CFTs, but as we will see, there are other examples, and they come from hyperbolic manifolds. And this will, in particular, allow us to apply the usual conformal bootstrap equations and constraints, linear programming, symmetric programming, to learn some new bounds, some new rigorous bounds on the spectra of hyperbolic manifolds. That's somehow the basic idea. Just as a quick introduction, let me tell you what I mean by the conformal bootstrap. So we'll be talking about the conformal filter in d dimensions. So small d will be always the dimension in which the CFT lives. And here is a possible definition of a CFT. So the basic set of objects which play a role are the local primary operators, which are denote OI. They're from some discrete infinite set. And they come with some labels, namely the scaling dimension, delta I, which is some real number, subject to various bounds. So delta is a scaling dimension, and rho, which is an irreducible representation of SOD, so some finite dimension of SOD, which is the spin of the operator. And this is the same data as specifying some positive energy representation of the Lorentz and conformal. Very familiar from CFT. So the next layer of structure on this is that we can do the OP, so we can take products of local primary operators, OI/OJ. It can be expanded as a sum over CIJK. So CIJK times the local operators, and the CIJKs, the structure constants of this OP, are also computed as the 3-point function, expectation values of products of 3 of them. And this set of data, the CFT data, consists of the scaling dimension, spins, and CIJK, and is subject to associativity, which is the statement that we can take a 4-point function and expand it in inequivalent ways as such. So we do the OP on IJ or IL, summing over M, and these two expressions must be equal, which takes a concrete form shown here. We have some equation where G's are the conformal block. It's an equation which is bilinear in the C's and the structure constants and depends very non-linearly on the scaling dimensions, which are hidden in these conformal. So this is what I mean by conformal bootstrap. If you wish, you can add some extra constraint, like for example, locality is the statement that the stress energy tensor, which is a particular representation, appears in the spectrum. You can also impose reflection positivity, which is some reality constraint on the C's and additional bounds on the deltas. But I'm not going to impose these two properties today. Okay, so once you have this kind of object, you can have some various hopes and dreams. And the main dream in the physics community is that some of these constants should be sufficient to completely characterize CFTs, in the sense that any solution of this complicated nonlinear set of equations corresponds to some CFT which is a physical mean. And we are very far from actually having any very good evidence for that statement. But if it's true, then one corollary of that dream is another dream, which is that some generic solutions of this set of constraints should be isolated, because generic CFTs don't have any exact marginal operators, so these solutions should be isolated. This may be something to try to prove. Another example of a hope is that there are no interacting solutions in more than 6 dimensions, and that's also very far from being on a solid ground at the moment. But the current status is that there's maybe some partial evidence that, for example, the 3D Ising model may be an isolated solution. So there's like a bootstrap island coming from these constraints, which shrinks very slowly if you just impose crossing of some finite set of correlators. But the idea is that probably at some point the shrinking will stop, and to really get an isolated point, we'll have to impose crossing of all 4-point functions. So there should be some the phase transition, then once we impose all four-point functions, we can see the discreteness of the space. That's
Even if that's true generically, do you really think it's true for the isomer? Because such a tiny region was found, just for the correlators that were looked at, to make it suggest that maybe it would converge to a point.
well, I'm not really sure what to think. I think that if we only include crossing of some finite set of correlators, then we do not get an isolated point. And I think there's a hope that if we impose crossing of all of them, then it's just an isolated. And maybe the setting that I'm going to explain today is a setting where such ideas can be tested concretely in this realm of hyperbolic manifolds, where we can actually we know exactly what the solution should be. Right, so, well, today I somehow like to take a different approach. So the main issue, well, one of the main issues is that we don't really have any explicit non-product solutions that we can kind of get our hands on in more than 2 dimensions besides semi-field theory. And it would be very nice if we could have some kind of a playground of actual solutions of the full set of equations. So not just the crossing of a single four-point function, but crossing of all of the whole mixed system of correlators. So to find some explicit solutions of that. And to do that, it would be kind of nice to have some mathematical machine, which if you like press a button, it outputs consistent set of CFTs. So spectrum, CIJKs, which solve this automatically. And that's what the conformal measure space does. So I'm not going to say anything deep. It's a very simple idea, but we'll see what we can say about it. So in the case of C, yeah.
In this setup, whether this G is a known function.
Yeah, G is a more or less explicit function.
So this is just an equation for the C.
It's
for the constant.
It's an equation for the C's and for the deltas. So the deltas are probably some transcendental numbers.
Okay.
Yeah, and so it's a nonlinear equation in the deltas and bilinear equation in the C's. But it's like a coupled system of infinitely many such equations.
I see.
It seems very complicated, but I'll explain a way to get exact solutions of this set of equations, or very similar set of equations from hyperbolic manifolds. Okay, so let's first ask, what is the machine that produces these solutions in the case of a CFT? And the way to sort of get consistent quantum field theories is a path integral. So path integral is a measure space. So you can already see where maybe this is going. So the idea is that the path integral is somehow a machine that guarantees consistency of a theory. So the first goal is just to abstract what we need from the notion of a path integral, that it is the guarantees consistency of Bootstrap. So how is the Bootstrap satisfied by the path integral, and what is like minimal set of properties of the path integral that we'll need? So the first thing that we'll need, I'm going to need a bit more space, so I'm going to write it here. Here, all the properties in one place. So the first thing that we'll need is just the set of field configurations, which for me, for now, is just a set. So I'm gonna denote it Y, and Y is just the set of fields. So set of field configurations, and I'm talking about the theory on RD or on SD. So CFT on SD. And I don't want to commit to any particular description of this set. Like, in the cases where CFTs have been constructed, this is usually some space of distributions, but I don't want to commit to any particular description. But what we want then is a measure. A measure on Y. So in particular, there is some sigma algebra of measurable sets and measure which assigns measures to the elements of the sigma algebra. And we'll normalize the path integral measure so that the total measure is 1. So we are kind of dividing by the partition function. And this is just the path integral measure.
So that not negative real.
Yeah. Yes, it's a map from the sigma algebra to the interval from 0 to 1, which respects countable additivity. Okay, so now let's just, what is an observable? Well, observables are measurable functions. So functions which make sense to be integrated. So there are functions from y to say complex numbers or real numbers, whatever you want, and the integral, the expectation value of such an observable is just the integral. Yeah, I'm not really saying anything very deep. I'm just simplifying what I mean by the which we can call elements of the field configurations, and this is how we are integrating the function. Now, so far, this is very generic. So let's put a little bit of the CFT in. So CFT means that the Euclidean conformal group. Let's take the connected component of identity, the Euclidean conformal group for concreteness. This group acts on the measure space. So it moves the points of y, it moves the field configurations around in a way that preserves the path integral measure. But by the way, so here, here I'm kind of putting the e to the minus s into the measure as you should. And G preserves the measure, so it acts on the thing in G, including e to the minus s. So it acts by measure preserving transformations on this. So that's how we are saying that this is a CFT. And finally, there is a slightly technical assumptions that this G action is ergodic. So what does ergodic mean? Ergodic is kind of the generalization of transitive. It's a statement that basically whenever you have some subset, some measurable subset of positive measure in here, if you move it using the G action around, you've covered the whole space. So one way to say it is that if you have a y prime subset of y, which is G invariant, then the measure of y prime is either 0 or 1. It's either basically empty or basically the whole space. And so I'm going to call conformal measure space anything that satisfies these four assumptions. And as I'll explain, these assumptions are basically sufficient to derive conformal bootstrap. And there are examples of these measure spaces which are not CFTs. They come from hyperbolic manifolds. This may be the most interesting thing that I'm going to say. But maybe let me just make a couple of comments. So yeah.
So so in condition 3, is there a way to distinguish G from an internal symmetry or a G which is a space-time symmetry?
At this level, no. I haven't. By the way, there is no space-time anywhere. I haven't made any statements about space-time, but as we'll see, thanks to the fact that we have this particular group acting on the measure space, space-time somehow emerges for kinematical reasons, because irreducible representations of this group, they can be realized as spaces of functions in RD, and this is how space-time emerges for any such measure space. So even for the hyperbolic manifolds, there will be some sort of space-time.
How is it guaranteed that the representation of G is not just like a fundamental representation or something like that? Because you don't, for the conforming group, you always want infinite image representation.
Well, okay, yeah, I think your question will be answered in like 5 minutes. Okay, so like I said, I'm not trying to construct this measure space explicitly, but the way you should think about it is that it's some gadget that's associated to a CFT, which is somehow non-perturbative and duality invariant. So if you say you have two different duality descriptions of the same CFT, they just give you two different set of coordinates on the same measure space. And I'm not saying that any CFT admits such a description, but I don't really know how to incorporate fermions into it. But I think that, for example, a critical 3D Ising model or the ON models, they should satisfy. There should be such a measure space. But saying that in the description, you can say realize the Ising model as a phi to the 4th theory, and then the idea is that we have some UV description, which is maybe some measure space. But what I'm talking about here is the effective IR description, where the conformal group acts on the space. So to start answering the question that Lawrence asked, whenever we have a conformal measure space, we can define the following Hilbert space. Which this actually makes sense for any measure space. We can define a space of L2 functions, which is just the set of observables that have a finite norm, where the norm, as you can guess, it's just the expectation value of that bar. And because of property 3, V is a unitary representation of G. So G acts on the measure by the transformation, so it preserves this norm, and therefore V is a unitary representation of G. But this is not the physical Lorentzian Hilbert space of the theory, it's some different Hilbert space, which is not a unitary representation of the Lorentzian conformal group, but of the Euclidean conformal. So V is a unitary representation of the Euclidean conformal group. For reflection positive theories, there should be some kind of analytic continuation of this Hilbert space to obtain the physical Hilbert space. I may comment on the at the end.
Excuse me, I have some question. So when you say the Y is a field configuration, it does a field is a limited space or space time? Because of this, the Hilbert space is just it's a space only.
It's a space. In the cases where this corresponds to a CFT, then Y is the space of field configuration in Euclidean space on SD. That's how you normally define.
No time direction.
Euclidean time direction on the SD. It's how you would integrate over all fields in the pattern. So for each point in Euclidean space, including the time direction, there's say some value of the field, and you integrate over all the field configurations.
Yeah, my question is about when you use a field configuration, suppose we have a space and a time direction separately.
No.
So whether this field configuration is a field on the space only or on the space time?
On space time, on Euclidean space time.
Okay.
So I'm not doing any slicing here. And this property 4, this ergodicity, is equivalent to the statement that you can start decomposing this into irreducible representations of G, and you can ask how many times does the trivial representation appear? And ergodicity is just a statement that it appears once. So the space of G invariant observables in the L2 space is one dimensional. 1, 4. So you can write it as the statement that the dimension of the subspace of V, which is G fixed, is 1, and these are just the constant functions. So this is just the multiples of identity. And but by the way, I didn't say that, but this property 4 is there to ensure that the Lorentzian Hilbert space has a unique bucket. Right. So far everything is kind of trivial, maybe you think, or one of the points that I like to make is that there are interesting examples of conformal measure spaces which do not seem to be CFTs, to which conformal bootstrap still applies, and these are hyperbolic manifolds. So how does that work? So it's going to be hyperbolic manifold, a D plus 1 dimensional. So what way to construct such manifolds is as quotients of the hyperbolic space. So we pick some discrete subgroup. Discrete subgroup of G. And then manifold M is just the is the quotient of the hyperbolic space. So this group acts on hyperbolic space on HD plus 1, and the manifold is such a quotient. Okay, then I claim that there is a very simple way to associate a conformal measure space to a hyperbolic manifold of finite volume, which is just take Y to be G mod gamma. So G is our group, gamma is the discrete subgroup. This is some smooth object, which knows about the manifold, because if we take Y and quotient by the SOD plus 1, then we get back M. M is just right. This right quotient is just equal to the hyperbolic space, because SOD plus 1 is a stabilizer of a point in HD plus 1. So the manifold is double quotient, but the conformal measure space is this. It's like a fiber bundle over the manifold where the fiber is SOD plus 1. It's a phase space of unit velocities of the manifold. Sorry, that's not. I think it's an orthonormal frame bundle is a technical term. And so what is the measure? Well, the measure is just the Haar measure. You take the Haar measure on G. And when gamma is discrete, this descends to a nice measure on Y, which is invariant on the right multiplication by G. So you can right multiply by G and everything stays. So if the manifold has a finite volume, then the constant functions are auto-normalizable, so they are inside the space. So yeah, finite volume you need for this condition, that mu of y can be normalized to be 1, and the action is transitive, so in particular it's also ergodic. It satisfies all the conditions from 1 to 4. And so the interesting thing that happens is that the spectrum of scaling dimensions, which will follow from the hyperbolic manifold, is related to the spectrum of the Laplacian octagonal hyperbolic manifold. So these spectra, in particular, they often exhibit chaos. So there could be maybe some interesting interplay between the properties of the quantum chaos for these Laplacians and maybe some chaotic properties of CFT spectra. But I just want to make the point that the spectra coming from these examples are still highly non-trivial, even though they are not as complicated as their CFT. But what exactly do I mean by the spectrum? So the spectrum is something that happens when you take the space of L2 observables and start decomposing it into irreducible representations. Spectrum. Anyway, maybe is it clear why hyperbolic manifolds give rise to conformal measure spaces? Should I say more about that?
If you had an actual CFT, what could you characterize why specifically?
Well, in some particular cases, these things have been constructed. For a free theory, Y is a space of distributions on the sphere or on RD. And then thanks to the work of some of mathematicians recently, like I think Shin was maybe in the audience, yeah, and his colleagues, Y and mu have been constructed for Liouville theory recently, rigorously. But for something like the 3D Ising model, it has not been constructed. And it's not even clear whether it exists. I believe it exists, but the jury is still out there. Yeah, I'm not really trying to. This is a very difficult subject of constructive quantum field theory, which was sort of stuck in more than 2 dimensions for several decades. So.
Is there some concrete description if you're given mu and y for deriving the delta as C?
Yeah, if you're that's what I'm going to say.
It will be the same for hyperbolic.
Yeah, the same prescription. Yeah. So the prescription is just to take the Yeah, right. So from now on, everything that I'll say will apply to all conformal image spaces, both the CFT ones and the one coming from hyperbolic manifolds. And in particular, the spectrum just arises by taking this Hilbert space L2 observables and decompose into irreducibles. So it's a unitary representation of G. Perhaps of this group. And these herbs have been classified. And here is a partial list, the list that will be important to us. There is always a trivial representation, which is just one-dimensional, C, and like we already saw, it appears precisely once in this way. This is ergodicity. So it appears once, it's just a constant function. And then the most important non-trivial class of representatives. Actually, all of the other unit representations are infinite dimensional. And the most important class for us are the principal and complementary series. So these are infinite dimensional, and they are labeled by the same set of data as local primary operators by scaling dimension and span. So delta is some complex number now, and rho is an irrep of SOD. And these representations can be realized as spaces of function. So this is where space-time first sort of emerges. So the way to realize this representation is a set of functions from the sphere, from the d-dimensional sphere, or you can make a stereographic projection and think of it as RD to the finite dimensional representation. So I shouldn't call it B of R, let them call it R. So R of R is this finite dimension irrep of SOD. So the P is just a space of some functions, which is infinite dimensional, and the two things I should say to complete the definition is how it transforms under the group and what is the inner product. But maybe I'll just say that it transforms like a conformal primary operator. Should I write it down? How it transforms? Yeah, I'll just say it transforms like a these F's. We take some G. So here is G maps F to some other function, and this new function is obtained. Maybe I'll write it down. So I can pick some bases. So these are basis vectors. A new function. This is the rotation matrix. It just moves the functions around. Where it is omega and R, they are defined by taking the differential of this map. Differential of the map is some d by d matrix, which decomposes as a scalar, as just a multiple identity, times a matrix in SOD. So there's a matrix in SOD, which corresponds to the fact that this function, the target here is a representation of SOD. And these representations are unitary for some range of delta and rho. So it's unitary on the so-called principal series. So when delta is d over 2 plus it, t is real. Or when rho is 0 and delta is between 0 and d. there's also, okay, so this completes the discussion of the principally complementary series. There are also discrete and complementary, discrete and exceptional series, but they won't really play a role today. If you saw my talk last year about similar topic, then I was using discrete series quite a lot, but today it won't really play a role. All right. So now what happens is that you can take the L2 space of the conformal measure space and decompose it into reducible, the trivial representation, and well, and there's direct sum or direct integral. Well, let me just write it. Let me write it what it would look like if the spectrum was discrete. There's some discrete. So there's a spectrum which emerges for every y and mu. The principal and complementary, so some infinite set of rows and deltas, and I'm going to write the discrete and contribution of discrete and exceptional series as just dot dot dot. Now I'm going to say when it's discrete and when it's continuous in a moment, but for now you just think of it as a cartoon for either discrete or continuous direct sum. Okay, and so when so this defines a spectrum, and it is dynamic, right? It kind of depends on y and mu, and I'll say in a second what the expectations are for various types of these measure spaces. But when a p delta rho appears in L2, we can construct this gadget which plays the role of the local operator for us, and it's something that takes an element in here. So the elements here are some functions. It takes a function. It's a function on SD or on RD, and it makes it into a function on the measure space. This map is supposed to preserve the action of G and the inner product. So now again, this was still quite abstract. Now let me say what is the expectation for the spectrum for the various types of measure spaces that I think are interesting. The first example is just some generic CFT that has light scalar operators, where by light mean that their dimension is smaller than d over 2. So the example one is a CFT with some scalar primary operator. Let's call it phi, such that the dimension of phi is less than d over 2. So you can think of, for example, sigma or epsilon in the 3D Ising model. Satisfy this property. Okay. So when you have such a CFT, which has a measure space associated with it, then you can construct various observables. Maybe the simplest observable you can construct is just to integrate the phi against some f. This is actually an example of this O map. So the O here, O is a map from the complementary series delta 0 to the space of observables. So maybe the value of phi at a point doesn't really make sense, but what should make sense is the phi smeared against some test function f, and as f ranges over this space over here, this observer ranges over all the possible linear functionals of the field. And you can check easily that this is actually L2 normalizable, which is guaranteed by this condition. So we'll just show it for concreteness. What is the norm of this in our L2 space? It's just O of f, O of bar, which is the same thing as dx1, dx2, d fx1, fx2 bar, and the 2-point function of phi. This 2-point function is just x12 to 2 delta phi by conformal invariance, and for suitably nice functions, and this is always finite because the singularity here is incomparable. This is not, of course, the most general observable for a CFT. In particular, you can also construct higher degree polynomials of phi. So the higher degree polynomials of phi, they will look like, I'm just going to try to explicitly, are these higher observables. So some function, just think of it as maybe a smooth function of compact support. Phi x1 to phi xn. This is also L2 because all of the singularities that you can get in the 2n function, they are at most of this strength. But these observables are not irreducible. So these linear observables, they correspond directly to one irreducible representation, but these ones you need to decompose further into irreducibles, and they will lead to a continuum on the principal series. So far the picture that we have for a general CFT is that this L2 of y mu decomposes like C, and there's some finite sum over complementary series. And then there is a continuum on the principal series, which comes from decomposing these higher polynomials of phi. So you should sum over the spins and integrate over the principal series. There could also be some degeneracy on the principal series, so that's tensoring with power of trivial representation and plus ... from the exceptional and discrete series, which I don't want to talk about today. This can be made super concrete for the only CFT that we understand in general dimension, which is the manifold theory. In view of time, let me just say the manifold theory in words. So in manifold theory, you can, let me just say a few words. In manifold theory, you can, you have this conserved particle number. The sectors, these observables are orthogonal to each other. They have a different number of phi's in normal order, everything, because you cannot. Yes.
Here, for all in CFT, it's SO2 harmony representation, but then when you use this product, you strictly change the reality condition, that's become SO1 of it. But if we start with we can do this because it's in the complementary series. What about principal series? Let's start with the principal series.
Okay. You're basically asking how do local operators in the physical in the Larsen Hilbert space emerge from the principal series? Yeah, it's a good question, and I wanted to avoid it as much as possible.
It's not a Hilbert space, right? It's not a Hilbert space.
Yeah, this is a Hilbert space. Yeah. It is not the Hilbert space of the theory on SD -1. It is a Hilbert space. Yeah. So far what I said makes sense even when the theory is not reflection positive, as long as there's a mathematical description. If it is reflection positive, then you can refine the construction in a way that maybe I can say at the end, which gives rise to the physical Hilbert space. And the complementary series, which are above d-2/2, become scalar operators. And the other local primary operators in the Larsen Hilbert space, they sort of arise from the continuum on the principal series. It's kind of poles, they're kind of like resonances. But it's a bit subtle. I wanted to get to some other things, but maybe we can.
Just to be clear, maybe you said it, so are all expectation values in the conformal field theory, expectation values of these observables are under the measure. So if I multiply the others under Correlation function.
Yeah, yes. I was going to define correlation function soon.
Okay.
Sorry, did you?
No, that's fine, if you're gonna get to that.
Yeah. So for metal theory, you can actually work this out very explicitly. And the answer is that, so for metal theory, you can check for yourself. This thing should be the same thing as a direct sum over n, from n to 0 to infinity, of the symmetric, so the Hilbert space, symmetric nth power of this complementary series representation. At least this covers all the polynomial functions of phi. And the different n's correspond to a different degrees polynomial of the normal ordered product of phi's. For n equals 0 and 1, these are irreducible. For n equals 2, it's no longer irreducible. But it decomposes on the principal series. You can see the principal series emerge very naturally here. So that was for the CFTs. Now, the example 2 is what is for hyperbolic manifolds. There, the claim is that this principal series representations correspond to Laplacian eigenfunctions. And one way to see it, so let's assume that P delta 0 is in our L2 of G mod gamma. Then you can decompose this under the reduction from SO1, D plus 1 to SO D plus 1. And you'll find the trivial representation appearing once, and then there are the symmetric traceless representations of arbitrary high spin appearing one. But importantly, there is the one-dimensional subspace of these SOD plus 1 invariant functions. So it's SOD plus 1 by rate multiplication, which means it's actually a function on the manifold. Right? Now, functioning here is actually a function, an alpha function here. So it's a function on the manifold. Only if you're in here. If you're in here, it's more like some tensor field on the manifold. And it's irreducible. So it's an eigenfunction of the quadratic Casimir of G. And the quadratic Casimir becomes the Laplacian on the manifold. So this F is an eigenfunction of the Laplacian with eigenvalue lambda, where lambda is the eigenvalue, is the quadratic Casimir. It's delta times d minus delta. And more generally, you can also do this for the higher spin principal series, and you'll find that the higher spin principal series in L2 G mod gamma correspond to symmetric traceless tensor fields, or to some tensor fields in some representation rho, which are divergence free and which are eigensections of the Laplacian acting on the space of sections.
Any constraints on gamma, or is it just any?
Certainly any discrete gamma of finite covolume will give rise to a measure space. You can even drop the finite covolume condition, and the identity will not appear in the OPE. The most general gamma that you can take is unimodular, meaning that G mod gamma has a Haar measure. That basically means that the Haar measure on gamma, the right and left Haar measure on gamma are the same. If you find this on gamma, this makes sense. When the hyperbolic manifold is compact, then we just get a discrete sum. So the analog of this decomposition for a compact hyperbolic manifold would be a discrete sum. So there could be some finite set in the complementary series, which precise values appear dependent on the manifold, and there is also some infinite discrete set in the principal series. When the manifold is non-compact, then there could be a continuum on the principal series. So in the case of non-compact hyperbolic manifold is a bit closer to CFTs, which themselves have a continuum on the principal series. Right. So finally, the correlation functions and the OPE. Do this relatively quickly because the formulas are the same as in a CFT. So we've seen them already. The correlation functions make sense for a conformal measure space. They are just expectation values, like Mike already said. They are expectation values of products of these OIs. So I can choose a bunch of functions in space-time in RD. Multiply them together and compute this correlation function. And because G acts by image transformations, these correlation functions are conformal invariant. So they look like just like correlation function in a CFT. So for example, the 1-point functions for n equals 1 vanish unless I is the trivial representation. 2-point functions. So let's just assume that I is a scalar principal series or complementary series. And just to make it super explicit, these take the following form. They're just dx1, dx2, f1x1, f2x2 times x1 minus x2, 2 minus delta I. For the n equals 3 case, we get a new piece of data, which are the 3-point functions. So now we have both the scaling dimensions and meaning of 3-point functions for a conformal measure space. So I'm not going to illustrate the whole formula, but you can imagine what it looks like.
Doesn't your formula show it only works for small delta? Because the interval when our conversion is delta small.
Well, it converges in the complementary on the principal series. I think it's conditionally converging on the principal series as well. As long as delta is not exactly d over 2, then it's a special case where it does not have a different formula.
I don't understand. F is a pretty general function of this one.
Well, say on the principal series, f should be an L2 function on RD with respect to the usual inner product on RD. Okay. Then when delta is d over 2 plus IP, this is conditionally convergent because it's an oscillating decaying function, so it converges. And then there is the usual 3-point function that we all know what it looks like in CFT.
But right at t equals 0, there is a logarithmic divergence.
At delta equals 0.
T.
Yeah. So yeah, the answer at delta equal d is just the delta. You need to replace this with delta function, and it works. Just this. For delta equals d over 2. And so for the case of hyperbolic manifold, the Cij case, they are related to integrals of products of 3 eigenfunctions. You integrate over the manifold for a scalar principal series at least. The Fi, Fj, Fk at the same point. There's also an OPE. To do the OPE, you can take two of these gadgets, OI percent F1, OJ F2. Now there is more subtlety. We need to assume that this is itself in the L2 space, which is true in the cases that are relevant to us. For example, compact hyperbolic manifolds is always true for smooth F1, F2. It's also seen to be true in a CFT as long as the O's correspond to the complementary series states. And so if this is in the L2, this product, so it's a function on Y. It's the function, the whole thing is a function on Y, measure the function of Y. So we can decompose it using this direct sum decomposition that we had before. And the coefficients are the usual Cij case. Then there is the OK. And the part of the image of OK, it depends on this F1 and F2, but it depends on it in a way which is fixed by conformal invariance. This is just a statement that the OPE is fixed by conformal invariance up to the 3-point function Cij. So you can write down a formula for this convolution of F1 and F2 using the conformal 3-point function. But so this F1 star F2 should be something that we can feed into OK. So it should be a function of on RD. And it's just this. Minus delta. Where this double angle bracket just stands for the 3-point structure. The specific function of x1, x2, x3, which is 3-point function. Okay, and finally, the 4-point function implements associativity. So the 4-point function, from what we said so far, it's a distribution on 4 points, or function of 4 variables. That's the distribution I can write as x1, the function of these x1 to x4. And using the OPE, I can expand the G into conformal partial weights. If you think this is kind of trivial, then I partially agree with you, but the part which is not trivial is that all of this also applies to these kind of new solutions of the Bootstrap, which are hyperbolic manifolds, and it also doesn't rely on reflection positivity. So it's a version of the Bootstrap that in principle should make sense also for non-unitary CFTs, as long as they have this path-integral description. Okay, so and this G, from what we said so far, can be written as a sum Cijm, CKLM of this double integral, so this integral of 2 3-point functions. Let me just write it as 1, 2, 5, and 5 shadow 4. So this is some explicit function of 1, 2, 3, and 4, which is equal to the sum of 2 conformal blocks. It's a conformal block of dimension delta m and spin Jm plus its shadow. Okay, so this is some set of equations. The equations are just the Bootstrap equations. So you can do this in 2 different ways. I can just say swap 2 and 4. And we get a Bootstrap equation, which is the same one that I wrote over here, with the small difference. Now the scaling dimensions lie on the complementary and on the principal series. And conformal block always comes with shadow. So it's not exactly the same as here, but here in reflection positive CFTs, there's a way to deform the integral over the principal series to be just a sum over the real scaling dimensions, the connection to the usual CFT bootstrap. So I think so. So it's some set of equations that constrains every conformal measure space, and I think it's an interesting question to ask whether, in some sense, it could be a complete set, but the only solutions of these bootstrap equations actually are the conformal measure spaces. There's a theorem, so it kind of reminds you of a theorem in one-dimensional algebras, which says that any abelian one-dimensional algebra, which acts on a separable Hilbert space, is actually algebra of bounded functions on a measure space. So what we are doing here is kind of like we are imposing the axioms of an algebra in the presence of conformal symmetry. And what one would like to see is that every such algebra is actually algebra of functions on a measure space. But it's not really a one-dimensional algebra, because in one-dimensional algebra, all the operators should be bounded. Here, for example, in a CFT, the observables like OF, the functions which are linear in the field, are not really bounded. I mean, to get bounded things, you need to exponentiate. You need to apply some bounded operator to the O of F. So that's why this is some possible obstruction in trying to prove that the only solutions of this conformal bootstrap are conformal measure spaces. Okay. By the way, a very simple example of all of this is when you do the hyperbolic manifold case, you choose gamma to be SOD plus 1, and the spectrum is just the scalar principal series. So the space of functions on the hyperbolic space decomposes like this: over 2 b over I plus infinity. And then these correlation functions, they are precisely the scalar contact within diagrams in hyperbolic space. We are integrating product of this O of F is the same thing as convolving for each delta in a principal series. We have an O of delta. We are convolving this O of F is like convolving F with the bulk to boundary propagator, multiplying them together and integrating over hyperbolic space. This is precisely the contact with the diagram. The simplest possible example. But notice that here I don't have any identity because the hyperbolic space doesn't have a finite volume. It's not really a conformal measure space according to the definition. Right, so I don't have much time left, but a couple of things. This whole reasoning suggests a new basis for the bootstrap, which is taking this as our bootstrap equation, and instead of evaluating it at a point, we can just choose the f's to according to our own liking. In the usual bootstrap, people choose the f's to be delta functions. Then you basic some derivatives of delta functions. Then you taking derivatives of the crossing equation at a point. But instead, it's nicer for some applications to take f's to belong to these SOD plus 1 irreducible subspaces. So, for example, when you take the principal series, it decomposes like that under SOD plus 1. These are SOD plus 1 symmetric traceless feathers. And we can choose f's to belong, for example, to R0, R1. Each 4 f's choose like that. Then you get some new basis for the bootstrap where the OP is truncated to finitely many spins. In usual bootstrap equations, all of the spins appear, but in this setting, you only get finitely many spins. So the simplest kind of sum rule that you can get in general dimension is a sum over all scalar operators. Summing over M, the external operator. So this is the simplest sum rule that's valid for both CFTs and hyperbolic manifolds. For hyperbolic manifolds, these are just summing over scalar eigenfunctions of Laplacian, where C is the triple overlap of eigenfunctions, and these are the Laplace eigenvalues. And for a CFT, the sum should instead become an integral over the principal series of the C delta 0. So C delta 0 is the spectral function that appears in the decomposition of a 4-point function. And we checked these sum rules to be true for symmetrical theory to the eigenmodel. And finally, some applications to the hyperbolic manifold. So let me just share my screen. Right, so what is going on here? Skipping several steps, but so this is a plot in the realm of hyperbolic free manifolds. So E is equal to 2. Is equal to 2. So we are dealing with these types of objects, hyperbolic free manifolds, and we are looking at the bootstrap of identical operators of spin 1. So this OI corresponds to the lowest Laplace eigenvalue on vector fields. And we are using the usual linear programming to put an upper bound on the lightest spin 2 eigenvalue. So spin 2 means in this case it's a eigenvalue of the Laplacian on symmetric faceless tensor field of rank 2. And on the very horizontal axis is so T is the parameter along the principal series. So the eigenvalue is real T squared plus 1, but the axes are the parameters on principal series. So this is the eigenvalue of the external operator. So the Laplacian on vector fields, and on the vertical axis is the Laplacian eigenvalue on symmetric traceless tensor fields of rank 2. And the dots are actual hyperbolic free manifolds. So hyperbolic free manifolds are isolated, use the most of rigidity, and using Hilbert trace formula, we computed these eigenvalues for a pretty large class of manifolds and just put them in this plot. So you can sort of see there should be an upper bound, maybe. It looks like for a given spin 1 eigenvalue, the spin 2 eigenvalue cannot be very large. You can sort of assume that there could be some bound. And then we did this bootstrap using the external spin 1 operator and put an upper bound on the spin 2. And this is the bound. And it's, you see, it agrees very well with the region populated by the manifolds. They're actually, the result of the bootstrap is that there cannot be any hyperbolic free manifold or conformal measure space more generally above this blue line, and it's true. There are some that come pretty close to it. Right, I'm already a bit over time, so. Yeah, just some open questions. So I think an interesting question is whether there are some examples of these conformal measure spaces which are not CFTs or hyperbolic manifolds, maybe something intermediate in complexity. Whether we can use this logic to put some new bootstrap bounds on non-unitary CFTs. And in general, if there are some interesting lessons that we can learn about the CFT spectra from the spectral hyperbolic manifolds, because they are both expected to exhibit chaos, and they are both subject to essentially the same bootstrap functions. So that's all I had to say. Thanks.
In the case of CFTs, it was important that you have reflection positivity and so on to get some bounds. Here you're getting the bounds without this constraint.
Right. So that's a very good question. Here, so for CFT which are reflection positive, and also admit this conformal measure space description, there are two different kinds of positivity. The reflection positivity, which is physical positivity of norms, states in this usual Hilbert space on SD -1, but also the positivity in the sense that I was using. That there is a norm on the set of observables, and this norm is sort of unitary for the Euclidean conformal group. So you can test whether this positivity is true for CFTs, this other positivity, by taking this function C delta J, properly normalized, and checking. Do you know what I mean by C delta J? It's this, so when you have some 4-point function in a CFT, we can decompose it as a sum over spin and a integral over the principal series. So it is the meromorphic version of the OP function. It is this function that just follows on the real axis where the local operators live. And the positive that I was using is that I was looking at this function on the principal series and checking whether it's positive there, and it's true. So for example, we check it for the 2D Ising model where the C delta J is known. For the mutual theory, it's also true. It's a way to test whether CFT admits this conformal measure space description.
I would have thought you'd say the following, that a CFT admits this conformal measure space description if it has an operator of low dimensions. Because then your definition of the inner product is not the usual one that uses reflection. But the usual one makes sense for operators of any dimension.
Yes.
Yours makes sense for operators of low dimensions. But if we consider the Ising model, since it does have an operator of low dimensions, one would expect one to not rigorously it's my prediction, but as physicists, one would say that it does have this kind of description.
Yes, yeah, I agree with that. And I wouldn't know how to create such a description for CFTs which do not have operators of low dimensions. Something else. I suppose there could be some object which makes sense as CFTs that even though they have operators low dimension, they actually do not have a positive mathematical measure. For example, the Liang singularity where there is some eyes.
So that's correct. So there are lots of quantum theories that do not have a positive measure. But the Ising model is not, for example.
So I think the existence of low dimension operator is a necessary condition, but it doesn't have to be sufficient.
Question and a comment. I mean, the question would be to try to make a concrete presentation for some complicated CFT, and I guess like the WZW level 1 where you have the free field description might be a very promising. Say you already have free field, and if you can fully understand that, right, you have to do symmetry. And then the other comment is that comparing the CFT and the hyperbolic manifold, and it's clear, it's very clear that the same formalism applies to both, but there's sort of a difference that the SO 1 comma D plus 1 symmetry is acting in some sense of the target space, and the hyperbolic manifold, if you try to make a unified picture where there's it maps from a base space of some dimension into a target space. CFT, you can get lots of CFTs that way, but you have hyperbolic space, you're getting the symmetry is acting on the target space.
But what is the target space?
Also, let me say where that question comes from, because the natural question will be, why are we restricting ourselves to hyperbolic manifolds? And there's a lot of from the point of view of quantum mechanics and path angle, that all makes perfect sense. It's quantum mechanics reference like manifold, but from your point of view, those manifolds don't have SO 1 comma D plus 1, so it's not really obvious what to do.
I don't think I have anything to add to that.
I wonder if you apply this approach to, say, 2D Ising model, can you get the spectrum of the scaling dimension, or whether some corresponding hyperbolic manifold which give rise to this spectrum?
I don't think that there are any examples of hyperbolic manifolds that actually secretly are the measure spaces for CFTs. I don't think that, well, it's actually, it's another question. Yeah. Could there be a hyperbolic manifold that's actually reflection positive and also local? So the two constraints that hyperbolic manifolds do not satisfy is reflection positivity and existence of a stress tensor. The stress tensor is a bit subtle because stress tensor is not a unit representation of the Euclidean group, but of the Lorentzian group. So it's more like a resonance from the point of view of this picture. But there are probably some theorems about locations of resonances, hyperbolic manifolds, which rule out stress tensor as a resonance. I mean, for the 2D Ising model, I would just use the ordinary bootstrap. This one, where we are summing over real scaling dimensions, and there actually people have done that, and they found that just like the 3D Ising model can be isolated to some approximation, also the 2D Ising model can be approximated, can be isolated. I don't think it's a theorem. It has been proven that the 2D Ising model literally saturates a bound, but it maybe can be done.
Another question is what this says about the deformations of this structure. So usually when you think of a measure space, you know, you can measure any place. And now of course your measure has to have this symmetry. So even so, you might think there would be lots of deformations. But is that true? Is it hard to find deformations of measures that respect this? Or conversely, are there lots of deformations, but they start to violate positivity and the physical condition?
I asked a question about.
Let's grant that there's this relation, CFT, conformal measure space. So now, from the conformal measure space point of view, what is the small deformations of a theory? And then usually, if you give a measure space, that has, you can deform it anyways. You can add, multiply the measure by anything, and that's a deformation. And so that would be a vast deformation space. And that contrasts with this, the idea of lots of degrees are probably isolated. And so is that a contrast, or is it that the SO1 comma D plus 1 symmetry of the measures is far more constraining than like this thought?
Yeah, I think the symmetry plays an important role. If you upgrade the ergodicity to transitivity, then the only such measure spaces are actually the G mod gamma type. Yeah. And then they are literally the same as manifolds. Those we know are isolated in more than 2 dimensions. So the symmetry probably is important.
So you wrote down an explicit Hilbert space for the case of mean field CFTs, right? So when you go beyond the mean field approximation and say like a CFT, how like where would the complication come in?
Well, the complication would be that would be in the spectrum itself. So the spectrum now will have some bunch of deltas on the complementary series that we don't really have explicit formulas for, and also in the inner product. So the inner product, in my formula for the mean theory that I wrote down, the inner product was just the symmetric tensor power of the inner product on the principal series representation, so on the single copy of the complementary series. But in an interacting CFT, the inner product on the space of functions, like on the space of polynomials of degree n, is equivalent to the knowledge of the 2 endpoint function in the interacting CFT. So that's some complicated function that we don't really know what it is, if say the 3D Ising.
Is the spectrum an input in what you did in defining this measure space?
No. Well, in defining this measure. So there is some general definition of what a conformal measure space is. And then the question is, what are the examples that satisfy the definition? And I give some examples, and I conjecture that some CFTs will give other examples. But once you have that measure space, in principle, its spectrum is determined by decomposing the L2 into irreducibles. So in that sense, the spectrum is not an input.
The spectrum is an output.
Yeah. it's some invariant of the measure space.
When you have a CFT that's more complicated, I think you're saying it, when you're trying to define the inner product on L2, that's where it.
There could be some straightforward supersymmetization.
Yeah, it's a question, right? But I mean, I don't really know how to put fermionic integration into the realm of measure spaces. But Pearson integration is not really a usual integration over a measure space. So I don't really know how to, I wouldn't know how to construct a positive inner product observable. Maybe there is a way to do it.
All right. Last question for Dalimil. Okay, let's thank him again.